Hello everyone and welcome to our final topic of grade 12 pre-calculus mathematics. Topic 12 is about permutations, combinations, and the binomial theorem. Some of these words a little foreign, but that's okay. We'll figure them out as we go along. I will say that this is probably my favorite unit. Honestly, I love perms and combs. Combinatorics are great. I will also say that it is probably the most different unit. It's very disjoint from a lot of the other things that we've done this year, and in that way it might be a little strange to adjust to, but it is a great thing. We'll be starting out with just learning how to count. And learning how to count when we're trying to figure out how many ways there are to do certain things. And with that, as an intro, let's figure out how many possibilities there are when a six-sided die is rolled and a coin is tossed. Woo! Okay. Well, a six-sided die gets rolled. How many options are there when that six-sided die is rolled? That's right! There are 6. So you have your little starting point here, and from there are 6 possible outcomes. Almost. Those are even enough. We have 6 possible outcomes. Maybe you roll a 1. Maybe you roll a 2, maybe you roll a 3, maybe you roll a 4, maybe you roll a 5, maybe you roll a 6. But then for each one of those possibilities with the die, there are 2 possibilities with the coin. You could roll a 1 and then flip heads or tails. You could roll a 2 and then flip heads or flip tails. You could roll a 3 and then flip heads and then flip tails. You could roll a 4 and flip heads and flip tails. You could roll a 5 and flip heads or flip tails. You could roll a 6 and flip heads or flip tails. Those are all the possible outcomes from this particular situation. We'll note that there were 6 possibilities for the six-sided die. There were 2 possibilities for the coin each time it was flipped. And all in all, this gave us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possibilities total. Interestingly enough, that happens to be 6 times 2. This leads us to the fundamental counting principle. And the fundamental counting principle, FCP, it's used to determine the number of ways a combination of tasks can be done. It states that if one task can be performed in m ways and another task can be performed in n ways, then the number of ways to perform both tasks is m times n. So we're multiplying the number of possibilities for each one of these tasks, and that gives us the total amount. We've got 5 examples to play with this for a bit. In this first one, a 6-sided die and we're tossing a coin. I think the answer is 12. But let's lay this out. What I like to do is have a slot for each event. Over here, we're throwing a 6-sided die. And over here, we're tossing a coin. For the die, there are 6 possible outcomes. And for the coin, there are 2. By the FCP, we are going to be multiplying these things. And 6 times 2 is 12. There are 12 possibilities. And we can expand this FCP to more than just 2 tasks. You can have 3 tasks or 4 tasks or 5, however many you want. The principle still holds that we're going to take the number of outcomes for each one and multiply through. So in this next hypothetical situation, some schmo named Mr. A has 15 suits, 50 dress shirts, 100 ties, 40 pairs of dress socks, 5 pairs of dress shoes, and 2 tie clips. Full disclosure, not all of these go together. For example, I would not, Mr. A, whoever this person is, that's not me, would not wear the pink pants with the green shirt and the orange tie. It'd be a heck of a statement and a real bold move, but probably a fashion faux pas. But how many outfits could we make if we have to get 1 suit, 1 shirt, 1 tie, 1 pair of dress socks, 1 pair of dress shoes, and 1 tie clip? Gotta keep that tie arranged neatly. Well, I'll arrange this the same way. I'll have some number of options for the suit, just 1 suit. I'll have some number of options for shirts. I'll have to pick out a tie. I'll have to pick out some socks. I'll have to pick out shoes. I'll have to pick out a tie clip. I have 15 suits, 50 dress shirts, 100 ties, 40 pairs of dress socks, 5 pairs of shoes, 2 tie clips, and multiplication in between all of those because of the FCP. Of course, this is all hypothetical. I've never actually done an inventory, or at least I haven't in a long time. So these numbers are not the truest. But in this hypothetical situation, how many possible outfits are there? 15 times 50 times 100 times 40 times 5 times 2 is some number. It's probably a good idea to tell you that this is, for the most part, a calculator unit. So whip out your calculator, punch some numbers in, and see if you get the same thing I get here. Do-do-do, do-do-do, do-do-do. Wow! That's a lot of outfits. I'm sure the vast majority of them aren't the best. For starters, I need to get a lot of those suits re-altered. Yeah, those pants fit kind of wide. Gotta get them tapered, you know? Anyways, more examples. See if you can try these, see what happens. The last 2 are possibly a little different, but you could for sure do example C. So feel free to pause, try it, and then resume the video and see if your answer matches up with the one I'm about to put here. 3 letters, 3 digits? This sounds like a Manitoba plate. Cha! We've got a letter, and then a letter, and then a letter, and then a digit, and then a digit, and then a digit. Ooh, ooh. There are 26 options for the first letter, and there are 26 options for the second letter. There are 26 options each time for the letters, all the way from A to Z. And for the digits, you could have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a total of 10 possible digits. And similarly, there's 10 possible digits, and then 10 possible digits. And by the FCP, these are all getting multiplied. Feel free to do that in your head. Feel free to process it on paper. Feel free to even use a calculator. And hopefully, you'll get a number that's sort of like do. Wow! That's a lot of license plates. How many people are even in Manitoba? I don't know. We've got a lot of people in Ontario, which is why Ontario also has 7-digit plates. Well, 7 character plates. What do they have? 4 letters and then 3 digits? I don't know. Ooh, but here, a restriction. So license plates that have no duplicate letters or numbers. So this is an interesting scenario. So we'll have a letter, we'll have a letter, we'll have a letter, and then we'll have a digit, and then we'll have a digit, and then we'll have a digit. Neat. Well, for the first letter, there's 26 options. And for the second letter, how many options are there? Not 26 anymore. One of those letters has already been used for the first time. So now there are only 25 options for the second letter. And then there are 24 options for the third one. We've taken that letter out of the bag. There are fewer letters left in the bag. And for the digits, initially there's 10 choices, but once that first choice is made, there are only 9 options for the next one and 8 for the one after that. That is really the key part in this. At this point, you understand you have to multiply all those options together. But making sure you can get those particular numbers down is what's huge. Of course, as you all know, we're going to multiply these. We're going to get a number out of here. So the majority of license plates will have at least one duplicate. If you want a fun challengey challenge, see if you can find how many license plates do have at least one duplicate. It's quite interesting to explore, but not something that we're at yet. How many ways could 5 people be seated in a row? Well, we have to put someone in seat 1. We have to put someone in seat 2. We have to put someone in seat 3. Someone in seat number 4. And someone in seat number 5. And with this one, well, how many people could we put in seat 1? I guess we have 5 options there. And once someone is seated there, there are 4 people that we could place in seat 2. And once those 2 seats are taken, there are 3 people that we could put in seat 3. There's 2 people we can put in seat 4. And then the last remaining person has to go into seat 5. And there's multiplication. So that's our general way to use the fundamental counting principle. One thing that's of note is that in these last 2 examples, we started to do some countdown multiplication. So we've got 26 times 25 times 24. It gets kind of cut off. 10 times 9 times 8, that kind of stops there. And this last one, 5, 4, 3, 2, 1, blast off! And we have a special notation to use when we have this kind of countdown multiplication thingy going on. It's an exclamation mark. It's an exclamation mark because this is, again, the most exciting unit. Oh my goodness. And the word for that is factorial. So when you see something like this, we're not just saying n! We're saying n factorial. I mean, you could be excited about it. You could put that emphasis in there. But you're not just shouting it out for the sake of shouting it out. You're shouting it out because of this exclamation mark. It has a mathematical purpose. And definition-wise, we're talking about the product of all positive integers up to and including n. So if you're talking about 10 factorial, you're talking about multiplying everything from 1 to 10, all the integers anyways. Or if you're talking about 20 factorial, you're multiplying all the integers together from 1 to 20. If you're talking about 50 factorial, then we're multiplying all the integers from 1 to 50. What a doozy. So 5 factorial is this one that we just saw a moment ago. 5 factorial would be 5 times 4 times 3 times 2 times 1. Everything from 1 to 5, including the 1, including the 5. The actual value of this is 120. I'm sure you're able to get that based on 5 times 4 times 2 times 2 times 1. The key is that you know that it actually is 5 times 4 times 3 times 2 times n. Similarly, 7 factorial, we're going to count down from 7 times 6 times 5 times 4 times 3 times 2 times 1. And if you multiply all that together, you get 5,040. It's pretty cool stuff. We'll note that these factorials kind of build on each other. Like inside of 7 factorial, we see 5 factorial. And even within 5 factorial, this part's 4 factorial, or this part's 3 factorial, or here's 2 factorial. Whereas 6 factorial, there it is. It's like 7 times 6 factorial is 7 factorial. It's kind of neat. There's always a build to those factorial values. One thing worth noting is that 0 factorial is a legit thing. 0 factorial is always equal to 1 because it's the number of ways to arrange 0 items. And because of this cool build aspect to things, it's possible to do some quick cancellations with division of factorials. Like if we have 7 factorial over 5 factorial, we can write it out long ways first. Where 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And 5 factorial is 5 times 4 times 3 times 2 times 1. But we can cancel those 5s, we can cancel those 4s. We can do all sorts of cancellation. And this is actually just 7 times, looks like a decimal. What am I doing with my life? There we go. Times 6. And if you want, you can say that's 42. Quick, try the next one. I dare you to pause this video and try it on your own. I'm going to do it now, so if you didn't pause, then, I don't know. Try it out next time, you know? Believe in yourself. Believe in the dream. Believe that notability will allow me to actually write the digit 5 and not turn it into an oval. There's a 6 on both top bottom. There's 5 both top bottom. There's a 4 both top bottom, a 3 and a 2. My goodness, look at all that cancellation. The result of this is multiplication of 10 and 9 and 8 and 7, but not 6. Not anything from 6 down because we divided by 6 factorial. So all those factors are gonzo. And this value is that many, apparently. Pretty neat stuff. And we've got this rule coming in here. N factorial is n times n minus 1 factorial. What does that mean? That means that 10 factorial is the same thing as 10 times 9 factorial. Or that 8 factorial is 8 times 7 factorial. Or that 4 factorial is 4 times 3 factorial. And we saw this evidenced over here. Here's 7. Here's 6 factorial. So you could say that, sure, 7 factorial is 7 times 6 factorial. We see evidence there. And to make that a more general case, dealing in terms of n instead, we write it out as follows. N factorial is the product of itself times the number that's 1 below it, times the number that's 2 below it, and the next number down, and the next number down, so on, so forth. And then eventually multiply by 3, and by 2, and by 1, and we're done. There's n. And the rest of this stuff is the product of everything from 1 to n minus 1. So there's n minus 1 factorial. So we can apply this division of factorials to even more general cases, ones that actually have variables involved. Like this, n factorial being divided by n minus 2 factorial. Well, that's like having n times n minus 1 times n minus 2, and so on and so forth. So we'll just say times n minus 2 factorial divided by n minus 2 factorial. But this cancels out that. So really, this is just n times n minus 1. We kept the n, we kept on n minus 1. We did not keep anything from n minus 2 downward. Just as up here, we kept the 10 and the 9 and the 8 and the 7, but we did not keep anything from 6 downward. We kept up here the 7 and the 6, but we did not count the 5 or the 4 or the 3 or the 2 or the 1. We divided by those. They gone. Ooh, try this last one. Looks like fun. That's the completion of that one. 1 less than n plus 2 is n plus 1. 1 less than n plus 1 is n. 1 less than that is n minus 1. And then so on and so forth. We can just say factorial at some point. Because there we have something same on top and bottom that we can cancel. We didn't expand and do all the collection-like terms, all that jazz, these examples. That's okay for now. This is not the end goal. These are all stepping stones that you'll want to be able to walk across with ease. So this is okay for now. I do want you to practice some stuff. Woo-hoo! A textbook. Yes, you can use this valuable resource. Practice a whole bunch of questions. And please let me know if any of those are a little too challenging for you, or if you have questions of your own that you wish to ask about them, or if I can offer any clarification at all. The end?